This is the last video on electric potential. Sorry, there's a lot, but it gets kind of confusing. Maybe you're already feeling confused, but let's start back with this picture right here. So we just finished up talking about this. So basically, the battery creates the voltage, in this case 1.5 volts. The wire doesn't use up anything. The bulb uses up that 1.5 volts of electrical energy. A better way of thinking about it is it converts 1.5 volts of that electrical energy into other forms, and then this other wire doesn't do anything. What if we had two light bulbs here? So let's change it. Here we have a 6-volt light bulb, and a 6-volt battery and two light bulbs. So here we go again, up our elevator in the battery. So we go from 0 volts to 6 volts. From A to B is just a wire, so we don't use up any voltage there. It turns out, as long as they're identical bulbs, that the bulbs then will split that voltage. So as we go through bulb 1 from B to C, we will use up 3 volts. So we will drop from 6 volts down to 3 volts there. And then as we go from C to D, which is another wire connecting the two bulbs, we don't use up any energy at all. And then we go through the second bulb, we use up the other half of the voltage down from D to E. And then from E to F, the wire doesn't do anything. We travel back to the negative terminal of the battery, and the whole process starts over again, raising us up 6 volts. So this thing that we always use up the energy is known as the loop rule. So that says that the voltage of the battery equals the sum of the voltage drops across each device. So if you have a 9-volt battery, no matter how many light bulbs you have in there or whatever they are, they're going to use up all 9 volts of that battery. They have to. This has a name. The name's not super important, but it's known as Kirchhoff's loop rule after this gentleman right here, Gustav Kirchhoff. And it's basically the circuit version of conservation of energy. If you give charges some energy by moving them up, but then they wind up back where they began, they had to lose all of that energy that you gave them. Think about it like this. If you climb up some stairs at a water park, if those things ever open again, and you're at the top of a water slide, you gained all this potential energy. As you go down the slide, you'll lose all of that potential energy. But if you walk back to the bottom of the stairs, you're right back where you began. So whatever you gained going up the stairs, you lost coming down the slide. So one last thing here is, we'll ignore this picture over here, is if you stack batteries, you actually add their voltage. So here we have 3 1.5 volt batteries stacked up together, negative side connected to a positive side. When you do that, you add up their voltages. So 3 1.5 volt batteries would be 4.5 volts overall there. The batteries in most of your devices are probably actually stacked. Like in your remote, there's probably 2 batteries. You don't realize they're stacked because they actually just like fold them up on themselves. But 2 1.5 volt batteries would be actually 3 volts that your remote probably runs on. So in your car is a 12 volt battery. Let's say one of these D cells is a 1.5 volt battery. Well, or a double A would also be 1.5 volts. If you stack up 8 of them, you would get to 12 volts. Car batteries are expensive, so why not just stack up 8 AAA batteries and use that as your 12-volt car battery? Well, this is a good review of voltage again. Why can't you do that? Well, the energy per charge in this arrangement up here would actually be 12 volts and okay, but we don't have enough charge inside of those batteries. So we don't have enough energy to get the car started. This battery has a lot of charge in it, and therefore it has a lot of energy. There's another thing we're going to sort of ignore, which is what's called the drain. These things just can't get the charge out fast enough. This thing, it's like it can open the floodgates and let it all out at once. And so that is the end here of our electric voltage video.